Sixth grade, welcome to lesson 2 in science here on this Friday. This week we ended with talking about what machines were, simple machines, what we're talking about, and the 6 types of simple machines. Now we're going to go through each one of those simple machines in a little bit more detail so you learn about them, and we're going to start today with levers. Our goal is what are the types of simple machines. There are 6 basic types of simple machines. Each machine works in a unique way to help you do work. Remember, work requires something moving. Okay, if you study the parts of any compound machine, you will find that it is made up of 2 or more simple machines. The 6 types of simple machines are levers, inclined plane, wedge, screw, wheel and axle, and pulley. And we're going to talk about all those today except the pulley. We'll get to that one next time. And so, guys, we can just put all kinds of these different machines together to get some of the more complex machines that you and I probably think of. Like a car engine has a ton of wheel and axle, spinning belts all over the place, different levers that would move things. All right, let's get started. What's a lever? The objects pictured on these 2 pages have something in common that helps make work easier. Do you know what it is? They all contain a simple machine called a lever. A lever is made of 1 or more bars resting on a support. You got number 1 in your notes. That support is called the fulcrum. Number 2 in your notes. The crowbar in the picture is a lever. The curved part at the bottom of the crowbar is the fulcrum. So down here, guys, is they're saying this right here, this F, that's your fulcrum. And if this was sitting on the ground, I would be pushing down on E. This is where I'm going to put the effort into it. And it's going to pry this big brick up. That's the load, okay? So the picture is only average because it looks like this stuff is just floating in air. So you got to picture like the ground going at an angle with this cement block here. And so this is sticking up. I press down on that. It lifts up the load, okay? The crowbar in the picture is a lever. The curved part of the bottom is the crowbar is the fulcrum. Sorry, I read that already. The cinder block, which is also called the load, this is what you're lifting, is on one end of the bar. It applies a force on the crowbar. In other words, the weight is pushing down on it. This applied force is also called the effort force. Oh, I'm sorry. Yeah, no, I skipped that. It applies a force on the crowbar. A force is applied to the opposite end, which then lifts that load. This applied force is the effort force. This is what we put into it. We put some effort into lifting it. When a person pushes on the crowbar to move something, the force created by the person pushing, which would be your effort force, will be less than the force applied to the load. But the effort force moves the handle a greater distance than the load moves. Okay, so we're going to pound this into your head over these next few days like we did yesterday. I have to put in less effort. So if I'm going to lift this thing, and I'm just going to make up numbers, if this weighs 100 pounds, and I'm only going to put in 20 pounds, that's 5 times less effort, which means I have to move it 5 times a greater distance. So guys, you can imagine pushing on this E way down here, and it's going to lift it 2 inches, right? So if I moved it down 10 inches, it would lift it 2 inches because 5 times less effort, 5 times greater distance. So mathematics class for today, inverse proportionality. As one goes down, the other goes up. Okay, the fulcrum of a lever doesn't have to be right in the middle. The order of the fulcrum, load, and effort force can be different depending on the type of lever. If the fulcrum is closer to the load, less force will be required to move the load, but the load will not be lifted as high. If the fulcrum is closer to the effort force, more force will be required, but the load will be lifted higher. In both examples, there will always be a trade-off between force and distance. If I need less force, I have to move it a greater distance. It's just that simple. That's how we do those things. Okay, so as one goes down, the other goes up. We have cruised through number 9 in your notes here. So the longer the crowbar is, the less effort it needs by me. So if I'm trying to lift this with a little short guy and I can't do it, I just need a longer crowbar. I am able to lift anything. I forget what famous scientist said. I think it's Archimedes. Give me a long enough crowbar and I could lift the world, which is true. You'd be strong enough to lift the world if you had a crowbar that, was 90 miles long or something like that. Simple mathematics, just needs impossibility. Okay, the 3 types of levers. This is what we're going to cruise through in 10, 11, and 12 here. First class lever. Can you find the fulcrum in the pair of pliers? So guys, your science book does a really good job with this labels here. So my fulcrum's in the middle in the first class lever. Loads are on opposite ends. In a second class lever, the fulcrum's at the end here, then the load, then the effort. In the next one, they have the fulcrum at the other end with the effort and the load switching place. So it went fulcrum, load, effort. Here it goes fulcrum, load, effort up there, but you can see the difference between, as we talk about this is going to be movement sides of it. All right, let's go through it. It's in the middle between the effort force and the load. So the effort force is the force you apply when you squeeze the handles. The load is the item which you grab with the nose end of the pliers. A first-class lever, such as a pliers, has an effort force at one end, the load at the other, and the fulcrum between them. So as I'm cruising along there, trying to fill in my notes, I would say the fulcrum is between the effort force and the load. What's an example? A pliers. Number 11, a second-class lever, such as a nutcracker, the fulcrum has an effort force at the end, the fulcrum at the other end, and the load is in the middle. The fulcrum of the nutcracker is at the closed end, where the 2 bars connect. The effort force is the force you apply when you squeeze the handles. The load is the nut that you try to crack. So you have this one, that the load is in the middle, and the example would be this nutcracker. Third, you probably don't think of a crab claw as levers. Can you find the fulcrum? It is the joint that connects the 2 halves of the claw with the crab arm. The effort is the force the crab applies with muscles in the middle of the claw. The load is the tasty morsel the crab pinches and grabs with the sharp end of its claws. A third-class lever, such as a crab claw, has the fulcrum at one end, the load at the other, and the effort force in the middle. So guys, it looks like it goes fulcrum, load, effort, but you got to follow this little arrow in here. Oops, and I just clicked that and I shouldn't have. Hang on. Okay, so you got to follow this little thing. It goes fulcrum, effort, load. And this one goes fulcrum, load, effort. Gives us greater distances to do those things. So you have this one with the third class lever. The load is at the other end. The effort force is in the middle. The example would be a crab claw. Levers, 3 classes of them. Cruising on to all the other ones. And as soon as I learn how to do this scrolling thing. An inclined plane. Would you rather carry a heavy box up a flight of stairs or use a ramp? A ramp is another type of simple machine. It's called the inclined plane. An inclined plane is simply a slanted surface. A ramp makes moving a load from a low place to a higher place easier. The inclined plane offers a trade-off between distance and force. You can see in the diagram that moving a load up a ramp takes less force than lifting it straight up, but the load travels further up the ramp. So in both cases, you will do the same amount of work. So if I'm strong enough to lift 10 newtons, guys, I would always just lift because it's a less distance. If I'm not strong enough, now I have to use a ramp, but I'm going to do it up a longer distance. Now, they said this statement. In both cases, you do the same amount of work. Guys, you know that's a lie. And it's simply a lie because a friction is going to waste energy. As I'm rolling up, this rolling friction applies into that. But in our simple 6th grade math life and science class, we just like to say, if I double the force, I will have to go half the distance. If I do 60% less work, 60% of the work, then I have to go 60% greater the distance, okay? So that's all they're trying to say with that stuff. So friction plays a role, guys. We just can't do math in 6th grade with figuring out the friction side of it, okay? So what did we do here? Number 14. The longer the ramp, the less force you would need. And so you just simply think about that today. Going into our school is a great example. I can run up 6 stairs on a building, or I can go all the way up the slanted sidewalk. Now that slanted sidewalk is going to be way longer to get me up there. Why? Because that's what we call our wheelchair ramps. And if I was in a wheelchair, I don't want a sharp ramp. I want one that's very gradual. That's a lot easier than me going up a steep thing. And so we made a law in America that says ramps got to be a certain distance or a certain height so that it's not too hard to get up there with a wheelchair. Not all inclined planes are as simple as a ramp. The left picture at the bottom of the page shows a part of a ship called the prow. This is what's sticking in there, okay? The prow is a wedge. A wedge is a simple machine made up of 1 or 2 inclined planes. The slanted edges of the inclined planes come to a point. Think of the bottom of a boat, guys, or you can think of this as the front of the boat here. This is the prow. To do its work, the wedge must be moving. So I can use a wedge as an inclined plane. I swing that wedge like an axe, it's now a wedge. If it's not moving, it's an inclined plane ramp. The force directed at the flat end of a wedge drives the point forward. The inclined plane of the wedge changes the direction of the force. A wedge can be used for splitting wood. So think of an axe, guys, and how we chop down on it. When I chop down, my force is going down. It pushes the wood apart. That's how we split wood. So what's it doing? It's changing the direction of the force. For digging in the ground, many sharp tools are made of inclined planes. Saws, knives, needles, axes. I move any of those, they're a wedge. So a wedge is a type of inclined plane. It's 1 or 2 slammed together, that is moving. Speaking of another type of inclined plane, the bottom part of the light bulb right here is another modified inclined plane. Thinking of a screw as an inclined plane may seem strange, but a screw is an inclined plane that is wrapped in a spiral. You're up to number 17 in your notes. The ridges of the screw are called threads. 18 in your notes. If you could unwind the threads of the screw, you would see that they form an inclined plane. A screw decreases force and increases distance. Screws often are used as fasteners to hold things together. Okay, guys, I have some examples of screws. So as you're looking at these screws, the 2 on the left are different than the 2 on the right. So these little ridges here, I'm just going to use this to point to it. These little ridges here, number 1 is the screw. Number 2, it's the inclined plane wrapped in a spiral. But these are what we call the threads. You can see these threads are spaced out much farther apart than these guys. So these guys right here, they're really close together. Now this is called fine threaded, like F-I-N-E. This is called coarse threaded, C-O-A-R-S-E, coarse threaded. Now I want you to think about this, guys. To move it this distance, now the screw's only an average thing because it's not quite the same distance as these threads, but I'm just going to show you the difference here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we'll go 11. I would have to turn this screw 11 times to make it move that distance. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21, I think. I would have to turn this screw 21 times to move it that same distance. This one is going to go more force because it's moving less times. This one would be easier for me to turn because I have to turn it a greater distance. I have to turn this guy 21 times, so I'm moving it a greater distance as I twist my fingers to do that. So coarse threaded is less distance, more force. Fine threaded, less force, more distance. If I was using a power drill, I would use this guy because I don't need to use the force. It would go faster. If I'm using my fingers, I would use this guy because it would be easier. You're going to need this on your test, guys. So write on your notes. Test. Fine is easier. And if you want a second thing, you could write coarse is harder. Maybe you want to write fine, less force, coarse, more force. Something to that effect, guys. So I can ask you what's easier to do work, and you know it's easier to do a fine than it is to do a coarse one. All right, let's finish it up. The wheel and axle. Did you ever ride on a Ferris wheel, similar to the one on this picture? If you did, you were riding a simple machine called a wheel and axle. A wheel and an axle is made of a wheel with a rod joined at the wheel center. You can see in the picture how much larger the diameter of this whole Ferris wheel is than the axle. The wheel turns through much greater distance than the axle, but the smaller turn of the axle is much more powerful. So I need a ton of energy to spin this little bar in the middle one time, and as I spin that thing one time, whoo, this big huge wheel goes around in a big huge circle. So they're saying this, in your car, spin that guy one time, spin your tire one time. Little distance, big distance. Little distance, lots of force. Big distance, less force. So in a car, lots of force supplied by my engine to move my car fast. And on a Ferris wheel, lots of force supplied to this axle moves the riders. We also do the exact opposite with a screwdriver. I'll show you that in a second. A wheel and axle can increase a force, or it can increase the distance to which the force acts. Think about a water faucet in the shape of a wheel that you turn with your hand. The force you put into turning the faucet changes into a larger force in the tiny axle, which opens the water valve. Can you imagine what it would be like to turn the faucet if you consisted of just the axle without the wheel? Okay, guys, that's going to look like this. Here's my little water thing. The pipe in my sink is literally about this big. Here is my faucet. I stick that thing in here so it meets up. Okay, now here's the handle of my faucet. Look how far I turned it. I turned it from way out here all the way to way down there. That's probably sliding it 6 inches. It moved this thing a ½ an inch. So this is how a screwdriver works, guys. I could turn it this way, right? Put it up and down like this, and now I only have to turn it a little distance. But this takes way more force. This, way less force. I can grab, I can turn, but I have to make this big, huge circle to do it. Okay, so that's what they're saying. On a Ferris wheel, the power's right here. I turn that thing, it spins my wheel up and around, and you go for a ride. Lots of force, moves a great distance. When I'm using a screwdriver, I want to be able to do this. So lots of times if I was going to put this into a piece of wood or whatever, I would start like this at the beginning. Easier, easier. The farther it goes in the wood, the harder it gets because there's more friction on the screw. Pretty soon I'm like, I can't do it. My thumb's not strong enough. Okay, switch, boom. Put it like that, and I can keep going. Greater distance, less force. So if you're using a screwdriver, guys, you want one that has a really wide handle, not a one that has a little itty-bitty handle. The longer the handle, the easier it is. Awesome. You got some help ready for a test. You got a few visuals that'll hopefully help you understand that to do those things. Speaking of a visual, I didn't bring it in, guys, but as I was thinking of pliers, one of the things I use a first-class lever for here is cutting tree branches. So if you picture this, instead of being something to grab with a little snips, this little guy you'd close with your hands, right? Now you also have ones that have really big long handles. The longer the handles, the easier it is to cut a branch. So if I was looking for a snips to cut tree branches when I want ones with really long handles. Longer, easier. Awesome. All right, have a great day, guys.